Hello, and welcome to the fourth part of Hexagonal Multi-surface Pattern lesson in Grasshopper. In this session, as before, we'll continue from where we left off in the previous part. We designed an isotropic grid of points, enhance it with the ability to specify divisions, add rows and columns, angular rotation, and weave a hexagonal pattern. And the script, let me remind you, is meant to generate a seamless hexagonal pattern across multiple surfaces. Today, we will move forward and add an optional feature that allows our hexagonal pattern to wrap onto itself seamlessly, making opposite edges match perfectly for any orientation. I mean flat top and pointy top and any division count. So that's the script we already crafted through the previous sessions. I will put a link to the description to this one if you want to follow along. And we ended up with the hexagonal pattern of points. So now, as I said, we will make a feature or an option to wrap this pattern onto itself. And first things first, we need to specify the direction. Now, in computer graphics in general, we agreed upon the fact that X direction is a primary one and Y direction is a secondary one. It follows. So X is the main one, and it relates to the UV coordinate space as well when it comes to the surfaces, and they are linked. So X direction in Cartesian coordinate space is a U direction, or equal to the U direction in UV space. And because of that, they are considered as a main, and we'll be wrapping we'll be wrapping our pattern along the X direction. And when it comes to the actual practical usage, we of course can easily swap the directions if we wanted to, but by default, it will wrap along the X axis. What does it mean? It means that we basically need to connect the end of our pattern, these zigzag line, to these zigzag line, basically merging them together. And by connecting them, what I mean connect them, it means that they're supposed to share the same position in space. They're not replacing one another, they are overlapping, basically stacking upon one another. And by the looking at this example, and by the way, let me just go in and add a little bit more points so that our grid will be a little bit bigger, so it'll be more visible for what are we doing. So I will go into the division X and division Y, right click, edit, and let me just increase it to 20. Why not? 20 by 20. Let me increase this. All right. So here you're going to see that we have these once again the borders, and you may imagine that we'll be, even though that we will be wrapping it, we'll be wrapping it in 2D. That sounds like a counterintuitive task, like why are we wrapping pattern when it's not on the geometry yet? But trust me, it's really beneficial to do it in 2D rather than in 3D. So once again, the task is take the zigzag line, all these points, and connect them to their counterparts to the left. So from right to left, basically weave the connection. So that will be basically another column of hexagons. But there is a problem. Actually, quite a few. First things first, the nature of a hexagonal pattern. A hexagonal pattern is a staggered pattern, and it has the stagger of even and odd rows, and the amount of them, with the 20 by 20, it's visible. The amount of elements in columns are different. So even rows for flat top are longer, and the odd rows are shorter on one. On top of that, they always have this shift, right? One goes up, then down, up and down, up and down, up and down. And that's the problem number one. The problem number two is the connections themselves. So if you look at this stuff, you're going to see that this is the actual connection which we're supposed to have. So this point goes here, this point goes here, this point goes here. Yes, it is diagonal. Right now you're going to see that there is a diagonal motion. Like Here, for example, it will not. But we'll talk about that later. But just the fact that we need to connect them is not very convenient, because every single one of those hexagons sits within its own branch. You already know this, because when we weave them, we have a lot of duplicates. Because, look, for example, this is a hexagon, and there is another hexagon, and there is another hexagon, and these points are not shared, because here are overlaps. So, for example, for these points we have 2, and for these hexagons we have 2 points as well. They are basically sitting on top of each other, right? This is really beneficial for the hexagons themselves, for what we need to do, but it gives us problems, because right now, to connect these points, I need to go to the different branches, because this branch with 6 points is different from this branch of 6 points is different from this branch, and so on and so forth. On top of that, we have duplicates. So I need to pick specific elements from the one, specific elements of another one, and here as well, do a lot of data management and actually make it work. Is it doable? Yes, of course. But if we will try to brute force it, like as we see it, and just try to connect it as is, it will become to be a more complex solution, because not only it will be different, because once again, this is for the flat tops, right? For example, we need to connect it this way. But if we have a different, let me just kind of do it here, just add additional column. When we add additional rows and columns, you will see that the points now in the different spaces, and their paths will be different. We need to account to that. And on top of that, if I will switch the type from flat top to pointy top, the actual connection is different now. It is at different points and at different points, and once again we have 2 branches, independent branches, and here we have 2 independent branches over and over and over again, which basically gives us results in a necessity to construct 4 different versions which connects based on the current situation. Is it an isotropic pointy top, or any pointy top, or it is a flat top? Is it staggered in one way, or is it staggered another way? How many rows and columns you have, and so on and so forth. That will be once again, if we go if we go with just a brute force method, we will try to do it as we see it, then it will become quite a painful process. Doable, of course, but just not very effective. But I would like to propose you a different solution for this. So instead of doing all of this data management to merge the points, find the proper ones, and so on and so forth, we will just take a last column, whatever last column is, we will take this, we stagger it manually. Well, like manually, we use, of course, a parametric solution for that. We stagger it one up, this is down, the next one will be up, and then copy that to the left side, up front. And that gives us an ability to construct the hexagons, which will not be like at 2 different branches, but the one branch here, right? Imagine that we'll move this to the right diagonally, and that means that the proper hexagon is right there, a full hexagon within its branch. And because we will be tossing it to the right and then to the left, it will have the same data structure, the same paths, and they will be basically identical. So it will be much, much easier to weave, and above all else, it will be a uniform solution. So it will be true for flat top, it will be true for pointy top, and with slight modifications, for the pointy top we need to pick the different order of points, because they weaved with a different order of points. But above that, everything else will be identical. So it will be just an easier solution. Remember, we don't need to work hard, we need to work smart. So how I will do that? Let's go step by step. So as I said, I would like to find the last column of this grid and then shift it to the right, one up. I can do one down, of course, but it will be more beneficial for me to do it this way. And you will see why. So let's go into our script. Let me delete this stuff. If you remember, that was for debugging our values for the our paths for the points. We don't need that anymore, so I just delete it. I will go in to the last node. Let me just put it like, I don't know, somewhere here maybe, and hide this for now. So this is my grid of points. Let me remind you how it looks inside. I will use the panel plug it in, and you're going to see that I have a data tree. Every single branch of this data tree is a set of 6 points, 6 points, 6 points, 6 points, 6 points, and so on and so forth. We need to find the last column. Which one is the last column? Well, if I look at this data, I will see that the maximum path, the deepest paths, is the paths starting with number 15, 15, 18, 15, 16, 15, 14, 15, 12, and so on and so forth, up to here, 15, 2. The previous one will be 12. Now, all of these ones, the last ones, they are the last column. This is the 15, 4, 15, 2, 15, 4, 15, 6, and so on and so forth. So this is the lowest one, this is the highest one. Remember, the grid starts from bottom left, so it goes like this, okay? So I need to somehow pick all of them at the same time, all 15th. And I will use the same node actually as we used before, this one, which called split tree, and we will be using masks again. Now here we already used masks, and I already explained that masks give you an ability to create a specific sequence or the rule, which will construct the proper paths, and that's why they're called masks. Like for example, here in the previous lesson we did this. We used a series of numbers, right? 0, 2 with a specified step, 3, 9 specified step, and that way we constructed ourselves a series of paths. Here we will use the masks again, but with a little bit different syntax. So how we're gonna do it? Now, first of all, I will just probably double click here to create a notch, and I will call that I know, let's call it base grid, this way. All right. Now I will use another split tree, this one. I will remind you, it locates under the sets, under the tree subcategory. Here it is. Okay. So I will put this into the data slot, and now I need to look at the mask. Now the mask is supposed to take these elements somehow. So somehow I supposed to say, give me please from all of this pool of paths and data, give me everything which starts with 15 and ends with whatever is inside, like everything which is inside 15. 15.2, yes, please. 15.4, yes, please. 15.16, yes, please give me that as well. And for that, I am use very specific mask. Let me show it to you. I will use it just temporarily to show you. So it's supposed to be the mask starts with 15 and anything within the 15. We have a very specific symbol for that. I don't know, by the way, how it's called in English, like a star. I don't know. So this symbol means that within the 15, it will find anything related to that. So if I'll plug it to the mask, click here, you're going to see that I immediately get the last column. And of course, if I will increase or decrease the amount of paths, you're going to see that it's not working anymore because it's not 15. Now it is 12. So we need, of course, to do it dynamically. How are we going to do it? Well, using the node called statistics, we already did it before. That's a debugging node, and I plug it to my paths. Oh, sorry, to my data tree, and here are my paths as a list. All right. Now, what we need to do is we need to take the last elements here, starting with 15. And to do that, we need just to find the numbers. So instead of a paths, I actually need the numbers, the list of numbers. So I'm going to say, hey, give me please the last one, right? But right now they are represented as a path. So we have a curly brackets, like, semicolon and other curly brackets. This is a string, or specifically this is a path. I don't want a path, I want a number. How are we going to do it? I will use the node called the Deconstruct path. I'm using the quick callout for that, and let me quickly check, did we use it before or not? No, we didn't. So let me explain what Deconstruct path does and where it sits. Now, first of all, it locates under the sets tree here in the bottom, Deconstruct path. It has a construct path opposite, replace path, and path compare. We will use all of them and a couple of them in this lesson. So Deconstruct path requires a list of paths. Here are our list of paths, and if I'll put it into the branch here and look at the indices at the output, you're going to see that what it does, it basically deconstructed the path on its depth numbers. So the first number, the second number, the first number, the second number. Like for example, here, the last one was 15, 18, right? Let's look at the results. 15, 18. Great. I need this number. How are we gonna do it? Well, I will take, I'll basically split these data tree by the first item and the second item. You already know how to do it because we did it before. I will use the list item node. Remind you, it sets under the lists subcategory in the set group. Plug that in. By default, the index set to 0, so we will take every first number in the list. Here they are, and this is our numbers. Obviously, they are now grafted, so if I really want the last of the list, I will flatten that. And remember, the flattening, grafting, and other operations, as I said before, has a quick access. So instead of going in and adding specific node, right, I'm going to do it this way. And now I have a list of elements. I'm sorry, so what element I need to do? The last one. And we know how to do it, so I'll use another list item node. Plug that to this one now, and by default it will give me the number 0, this one, right? But I need the number, the last number. This is the first number, I need the last number. Two ways of doing that. I can type, and I already explained it to you, -1, and plug it into the index. It will take me the last one automatically, 15, this one, like this. Or I can just detach it, delete this, and instead of using this list as it is, and by default it starts from the smaller number to the bigger number, I will reverse the list. So I will go in and I would say reverse, and it will automatically give me the first element in the list. Now this reverse item, once again, this is another quick call out, and we have the proper node here. So if I'll type reverse, reverse list, I have this component, and this is its shortcut. The reverse list sits under the list tab, I believe. Actually, I don't really remember, but I believe it is. Yeah, reverse list. Here it is, right? So this is a quick access to that. And now we have the element 15. So basically, we took the list and inverted that. What was first come last, what was last comes first. And because this one by default takes the first element in the list, one locally defined value, 0, it goes to 0. In the reverse list, it will be the last number. All right. Okay, so now we have the number 15. But that's not exactly what we want. We want to have a very specific construction here. 15, and then these, once again, I don't know how to call it in English, this symbol, like a star, right? How are we going to construct this from this? Well, that's where, because it is a path, there is a specific node here which called construct path. But this node will not help me because it requires indices. This is not an indice. So if I will plug just the number here into the construct path, it will give me the proper syntaxes. But I need this one. And because this is not an indice, I will not be able to use the construct path node. What's the workaround? Well, the workaround sits under the text subcategory in the set group, and it's called concatenate. Here it is. It basically concatenates or join together different fragments in a form of a string. It can be a number, integer, a string, everything you want, and it can combine it in something, like in some kind of a string list of data. So I will take, and I need just to do it manually. So if I look here, we start with a curly bracket, right? So the first fragment will be a curly bracket. Let's place the curly bracket. Let me right click, delete the title, so it will be a little bit shorter and compact, like this. It will be the first fragment. The next fragment will be our number. We already have now our number, here it is. Let's plug it into the B. Let's look at the result. Okay, we're getting somewhere. What's next? Semicolon, star, and another curly bracket. And we basically do just let. So let me Ctrl-C, Ctrl-V, I'll just duplicate it, and I will type semicolon, star, and closing curly bracket. And then I will get additional input and plug that here. And you're going to see that now we have the proper mask for our node. All right, simple as that. So what we're going to do next, let me organize it just a little bit. Let's put it up. Let's put this one down. Maybe something like this. Like this, right? Let's delete this. Let's make it a little bit more compact because we'll have a lot of nodes today to place. Like this, maybe. Like this, and I will plug that into the mask. Click, last element. And now if I will change the amount of divisions, you're going to see it's not breaking because we automatically detect the last column. Perfect. So now we have this last column, and as you can see, it starts with 15 because it was the last one, and that's everything within. Once again, it starts from here. This is the first one, second, third, fourth, and so on and so forth. Okay, so now we effectively selected automatically, or parametrically better say, the last column. What we need to do next is we need to take this and shift it in the stagger manner to the right. So how are we going to do that? There are multiple ways of doing that. Now, first of all, we are operating with points. And the points are a list of 3 values: X component, Y component, Z component. If you watch my previous lesson, you know that they actually are numbers, and at the same time they can be represented as vectors as well. So we're going to use just the components and just the raw numbers to find the proper positions, calculate the distances, the absolute difference, and then add them up and move it to the right. It will be really, really manual solution. Pretty cool one, but a little bit like, I don't really need to do that because we have a lot of nodes which actually can operate with this geometry as a whole. Now, most of them are located under the transform tab in the Euclidean transformation set. So we have move, orient, rotate, a few other ones which are actually very useful, and we'll be using them a lot. And they all sit in the Euclidean transformation because they are all the parts of Euclidean transformation, something we can represent as a matrix, or transformation matrix, this one, in Cartesian coordinate space. And in fact, these formulas which we used for rotation is actually a part of these 2D transformation matrix. That's why they have this very specific representation. And all of them are actually the same. Like, for example, the rotate, this command actually can be used to replace these ones, by the way. But I didn't use it. We will use it later. I didn't use it because I don't want to construct the points, and I work with the raw numbers, and these one required the geometry. But I digress. And a part of these ones, we have a very specific two. One of them called the move, and another one called orient. Now, the move command takes the geometry, or basically our set of points. It can be any geometry, not only the points, and it asks for the motion. This, if you hover, you're going to see that there is this arrow in the hexagon. It means that this is a vector. It requires a vector. So I need to construct a vector, or specify the vector of motion, and I'm going to take my geometry and move it effectively using this. But to do that, I need to construct the vector first. Effective, but once again, we need to do additional step to construct the vector. We will use it later, and I believe I even use it in the first lesson just as a demonstration. We will use it more extensively a little bit later. Another one, and the one we actually want to use here, is this node. Amazing, fantastic node called Orient. It not necessarily moves, it orients geometry from one place in space to another place in space. It looks for the geometry, and because we can work with any geometry, and it asks the point from which you want to move. Like, imagine that I will look at my set, I will click on this point and drag all of the construction through this pivot to something else, like for example here, right? And that's what it does. But the source and target, if I'll hover, you will notice that it says that it requires a plane, initial plane, and the target is a target plane. I didn't explain planes yet. There will be time when I will do it and we will look at this node differently. But for now, what I want to say is and this is not a coincidence, you can plug points here, not necessarily planes. As I said, this is not a coincidence because automatically a point is a part of the plane. And Grasshopper, if you plug the point, it will automatically design a local plane which will be oriented in X, Y direction. Now let's look at our viewport. We are constructing the grid in the top view, meaning that we are in X, Y planes here, X, Y. So we are already in the XY plane, and if I will plug the source, it will be oriented the geometry in XY plane, basically the way how it is right now. So that's not an issue. So what I'm gonna do for now, once again, we will talk about this and I will explain all the beauty of operating with planes and this node in details when it comes to the 3D, but it's really useful already now. So I will take my geometry, like for example this one, and plug it into geometry. And then I need a source and a target. What is the source? The source is the pivot point, or basically the point from which I want to grab and move, right? And the target is where I want to move it. Let's look at our elements. Now, at our tree. Now, our tree consists with branches. Every branch consists of points. So what I want to do is I would like to take, in this situation, I would like to say that this point, I would move it from this point to this point. And if I will do that, it will stack one up staggered. How are we going to pick this point? Now this point, of course, is the first point for every hexagon. Why do I know this? Well, because we weave it. We weave it using the relative item the same way. So I know that this is the first point. You, of course, can check it quickly using list item node and go through them and see which one will highlight it. Or, let me show you, this is a good example and good demonstration. We can go to the display tab. And in the vector set, click on this one called point order. This is a debugging node. You can see it doesn't even have an output, but it has an input. And if I'll plug my points, the list of points, the data tree into the points, you're going to see that it will construct me these lines. They are actually the representation of vectors, and it shows me the order. This is the first one, this is the second one, the third, the fourth, the fifth, the sixth. The first one, second one, third, fourth. You're going to see that they're overlapping here because these points overlap these one, or better say, because the order goes from bottom up, it means that this one overlaps this one, right? So this is the first one. So I know that for the source, this point is the first one, and it's really easy to call it out because just through list item. So I'm using the list item, plug that in. By default, it takes the first point in the list. Click. Let me just kind of hide this right now. So click, and you're going to see that we immediately highlighted the first element in the list. So this is our origin. Once again, in 2D, in proper orientation, it will automatically, through this point, this node will construct me a plane. How to construct the planes ourselves, how we orient them and work with, using this node, we will talk a little bit later. So I will use this one as the source. What is the target? Target's supposed to be this one. Which point it is? 0, 1, 2. This is a third point, but because we start calculating, counting our list, this is indices with 0, remind you that it will be the third point with indice number 2. So it will be another list item, and this list item will be 2. Now, am I correct or not by picking this item 2? Because I said it like it's supposed to go here and we will get the proper result. You probably don't question me, right? But if I will plug it here and look at the index 2, click on this, looks like it is a pretty legitimate point. So this is the start, this is the end. If we will move it, it's supposed to move in the proper position, right? Well, let's check it out. So I will use my my data tree, plug it into the geometry. I will move the source. Let me just turn that off, Control Q. I will put this one into the source and this one into the target. Supposed to be in the right place, right? Let's check this out. Yes, indeed. So now we moved it one up from here to here, and all of my points are shifted one up. Cool. Let me go in here and adjust it a little bit. Let's delete this and do it like this. Okay. Now I would like to remind you, and I believe I said it before, that if when you construct your scripts and you know that some of the values you will not change, use panels, not sliders. It will be easier for you to understand that you don't need to change the value. It's hard-coded into the system. And this value, indeed hard-coded, it will always, for flat top, for pointy top, it always will be 2. Let me actually delete this. But this number is not. And I said, and I mentioned that the solution which we'll be using is uniform for a flat top on the pointy top hexagons, but the actual point order is different, meaning that when we go to the flat top, this point will be different. We will not pick the first one, we'll pick some other point. It's pretty difficult for you to understand which one, but it doesn't matter. Right now, we will do it later. For now, what I want is I would like to, right now, right from the get-go, bring a switch. Because we have here the original switch, which changes the orientation of our grid from flat top to pointy top. And I already have the gates, which works in tandem to switch our masks, so it will work. Here, with this value, I need to do the same, because when it is a flat top, a very specific value is supposed to be brought here. The first element will be the 0 element. And for the pointy top, it will be something else. So let's bring it right away and create a switch. So I will type filter. We already used it before, stream filter. We already have the gate. So if I'll plug this here, the same data, let me kinda probably do it something like this. I'm using notches to adjust the placement of my nodes, so it will be a little bit more organized. Now, this path basically gives me the same values as my switch 0, 1, 2, 3, if you remember. Let me remind you. Edit 0, 1, 2, 3. So the flat top is anisotropic and is isotropic, which means it's 0 and 2. And pointy top is 1 and 3, right? That's why we have 4 inputs. So I'll do the same here. We need to have 4 inputs. And the first value, which will be based on the selection of a type of a hexagon, is this value, the first element. So I will go in and I will plug the value 0. Let me shrunk it, and I will type flat, because I know that that will be for the flat orientation. And I'll plug it in 0 and 2, because both of them are flat top, anisotropic flat top and isotropic flat top. And I will plug that right there. Now, of course, it doesn't change the output now, because we are in a flat top. We're picking the 0 element. So basically, nothing changed, but we give ourselves an options to bring different value for the pointy top. All right, so here is our new column and the new data tree. That was the last column of the original data tree and our original grid. This is an addition. Now this addition is temporary. We don't need all of that. We need only the last points. And I would like to mention that if I will use the panel to see the data structure, you will notice that something which I said before, and which is crucial for things to come, is that these data trees has different points, right? The points are different, but the paths and structure is absolutely identical. And that's not surprising, because when we perform an orient operation, we took existing geometry and move it somewhere else, or reorient that, but we didn't change the actual data structure. That's why it stays unchanged. So now we have 2 data trees which has absolutely identical paths, but a different content. That's exactly what we want, because what we need to do now is we need to take these ones, the actual ones which we moved, and toss it to the left. And when we will do that, we will have 2 identically structured data trees, and it will be very easy for us to weave the elements, because right now we'll be weaving these 3 points with these 3 points, and they will not be in the different branches, but they'll be in the same branch, right? When I'll move it right there. That's the beauty of that. Let me show you. So how we move it to the left. Well, to do that, using the same command orient, I need the origin or the source of movement and the target. Now, to find the target, we first need to find the first column in our data tree. How are we going to do that? Well, let's go to original one. Here's the original one. Through the deconstruction of the path and constructing a mask, we found the last one. But finding the first one is much simpler because the first one is always the first one. So what we're going to do is we use another split tree command. Let me organize it, so I'll plug that somewhere here. Maybe I'll organize it this way. Now, in general, when I do my scripts, I'm not bothered about the, I often do just a crazy spaghetti code. And then when everything is done, I'll go in and clean it up. But I really want that it will be, logical and structural for you, so it will be easier for you to understand what's going on. That's why I'm spending additional time right here when we're creating the script to do some cleanup. So this is still our data tree. It goes to the notch and still bypasses. This goes to this notch, and we will go to the next split tree command. So let me remind you that we have for this tree a set of paths, see? And it starts with the first element, which is the first element, the 0 element. So if I will go in the mask, just hard code a mask 0, everything, it will look for all the elements with the path of 0, with the first number of the path of 0. And it will always be the first one in the list. Very convenient. So let me delete the name. Once again, I want it to be compact, right? And let's plug that somewhere here. So now we have a first column of our grid. What we need to do now, we need to find the proper point. Which point for orientation of this newly created column here will be the proper one? Is it this point? Is it this point? This point? Which one? Well, if you look at this, the first question is, okay, what is the source point? From which point we move it? Well, the proper point will be this one, because you're going to see this is like this kind of zigzag line. So if I'll take it here and move it right there, it will perfectly match, right? But remember that I moved this one up, so I need to make this one up also, right? So basically, when we're doing that, this point is not supposed to be here first, it's supposed to be here. Meaning that we need to make a very specific point for the end position. So the end position here will be, let me see. So this point is the 0 point. Then this is the first, the second, the third, the fourth, the fifth, the sixth, the same thing as everywhere else. So we need to take 0, 1, 2, 3, 4, 5, 0, 1, 0, 1. I believe we need to take the element number 1. So let me try it out. So I will go in and I will type a list item, plug that in here, and I will type the first element in the, sorry, not the first element in the list, but the first, this one, the second element in the list, this one. All right, once again, this is 1 because we start our list with 0 all the time. So let me remove the title. Okay, yeah, and that was the right point. You're gonna see here it is, here it is, here it is, here it is, one up, not these ones, but these ones. So this will be my end point, and these will be my my origin. So let's take the origin. The origin will be 0, 1, 2, 3, this point. So we'll go in and we'll type list item, and we will type the path 0, 1, 2, 3. It will be the path, the number 4. Oh no, sorry, it will be the number 3. I made a mistake. This one. All right. 0, 1, 2, 3. Yeah, of course. All right. So we have the origin or the source, and we have a target. Let me just arrange that a little bit again. me maybe align it this way, like this. Let me move it somewhere here so it'll be closer together. Okay, and now we'll use another orient command. Orient. Our geometry will be this one. So this is the newly created one which we already shifted. Now we put it to the left. So geometry, source, this point, target, this point. Bam. Perfect. So we took the same column and move it to the left. But there is a catch, and I would like to point your attention on this. Let me hide it for now. Look at the amount of points which our source and the amount of points of our target. How many points do we have here? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. 10 points. How many points we have here? 0, 1, 2, 3, 4, 5, 6, 7, 8. We have one element less. Shouldn't that be a problem? Well, actually, kind of supposed to be, because we have less amount of points on one side and more amount of points on the other side. So we somehow need to balance them out. So the amount of points from which we move, where we move, as well as the geometry itself, how many elements we toss here, supposed to be identical. All right? You already know where it's going. We, of course, need to use the longest list command. I explained it before. I quickly just remind you again that because this is such a crucial component. So the longest list, this is the shortest list, this is the longest list. I'll plug both of them here, and in the output, the new list. Let me look at the new list here. You're gonna see that this list now has, let me go and quickly go through the statistics, plug this here, and look at the count. Here, 10 elements in the list. So this one was 10 and stays 10, these ones. These, the origins were 9, and now they become 10. You already know how the longest list works. It repeats the last element in the list if it is shorter. So now we have 10 elements in the list. So 10, 10. What's about our geometry? How many elements we have in the geometry? 9. But if we'll plug that here, we will get ourselves 10. It will take the last element, which is this one, and duplicate it. So now we have the perfect pairs. And then you plug that into the geometry. But as you can see, I never did that. So my geometry works perfectly. Why? That's another example of yet another node which has data matching built in. I mentioned that every single time we encounter that. I point it out, and this is yet another node which of course has data matching built in. That's why it's just so important. That's why you don't see an error. Everything works perfectly. There was less amount of elements. There were more amount of, there's supposed to be more, and no problems. We have all of them here, and here they are. Because this automatically matches the amount of elements by just duplicating the last. Okay. So, all right. So now we have the specific list of elements, which is actually now has the same not the same, but it just has more outputs, the more branches than the original one. And you're going to see that now it's poking through the grid, which will definitely get me an error. But right now it does so. But if I will go in and change the order or change the amount of division so that the last one will not be this one, but it will be this one, right? So let me just, for example, add additional X. Whoop. Well, now that's perfectly fine. They are doing the proper thing. So we need to have an expression, basically an if-else a Boolean operation, and we need to figure out if the amount of elements here is equal to the amount elements of here, just don't do anything. It's already nice. But if this length is longer than this one, cut the last one, please. Let's do that. It's quite simple. So we have ourselves this list of data, and the data tree. I will use this statistics node, plug it here, and look at the count. Count is 10, right? What's about this one? let's repeat the same step, plug that here, and look at the count. Count is 9. So when they are different, all right, and once again, they are different because this node automatically figured out that they're through the longest list operation that the amount of amount of targets is bigger than amount of sources. So we add additional one automatically. Now we have more elements in this group, right? So I'm kind of reiterating that again. Yeah, probably supposed to stop. So so now they have these two values, 9 and 10. And basically we need to say if these numbers are equal, just do nothing. And if one of them is bigger than another one, then please take this row, the newly created one of this data tree, and remove the last branch. Once again, this is the first branch, this is the last branch. How are we going to do it? Well, we have a very specific set of nodes. It operates with Boolean operations. This is, of course, the standard Booleans. There sits under the math tab in operators is these ones, and we have gates and nor, orcs, or nor, NAND, and so on and so forth. We'll go through most of them along the course, but for now we need just the standard equalities. So if I will use the equality operator right here, and I would say that the first number, let's say, is, it doesn't matter which one, like 9, and the second number is 10, and we look at the output equality, it will say false. This is a Boolean. And basically, Booleans in Grasshopper, in programming in general, is equal to basically two numbers. False is 0, true is 1. So it says false. And we're going to use this as a gate. Alternatively, instead of doing this big node, I'm going to use just expression node. And in the expression node, I will just type x equal y. And I will plug x and y, and I will get the same Boolean result. All right, so this is false. This is our expression, and it gives me the false result. And when it gives me the false result, I need to go in and remove the last one. How am I gonna do it? I will go in, take my last or my first new column, right? This one, and I need to eliminate the element 15, 19. That's this one, the last one. How gonna do that? Well, actually, very simply, we already use the node statistics to figure out the count, the amount of branches here. And we're gonna use the path instead. So we look at the paths, and it gives me the list of paths. Right? We already did it before, so you know what to expect. Now what we need to do is we need to basically remove this one from the list. Not reconstruct the tree, but say, hey, give me the same tree, but without the last element. Can we do that? Yes. Multiple ways. We can use the node called shift list. I will explain it later. But I believe that the good start is to get to the sets and open up the sequence tab. And in the sequence tab, you're already familiar with this because we use series. There is this one, which is called Cull Index. Let me bring it in. So the Cull Index requires you the data tree, and this is our data tree with the paths. Unplug that in here. Then it requires the indices. It can be one index or many indices, which you want to remove. Which one I want to remove here? The last one. Which is the last one? Well, the last one. All right, let me do it now this way through the -1. And if I plug it in, bam, it's gone. It gives me the output with removing the indices, and give me the output of the same data tree with the indices we specify to remove, right? Okay. And of course I can reverse the list and don't use the index and use the index 0, but you need to specify, oh, sorry, you need to specify the indices here. You can't leave it untouched. Because by default it doesn't have a value, right? So you still need to place the number yourself. It's not like a list item node. All right, so now we have the last amount of paths. What we need to do next? Well, in the previous lesson, I already introduced you to the node called tree branch. It locates in the tree here, tree branch. We used it to construct our own cluster. Remember, we used the branch slider, branch slider, this one, and I explain how to do the clusters. This is a really good feature for analyze the data trees, right, which we did in the previous lesson. And we use this data, the tree branch node. I remind you what it does. It takes the data tree and on the input and basically sort it through the paths. This is not a mask. This is just the actual paths. It doesn't take masks. So here we have the list of paths, and it basically says, give me the data tree, visualize me the new data tree with only specific set of paths from the original one. What's our original data tree? This one. Let's plug that into the tree. Which our paths we want to visualize? These ones. We removed one. Plug it into the paths. Click. Here they are. And basically we effectively removed one, right? Okay, we removed one, but now they are disconnected. The expression and our boolean is separate and the branch is separate. So now we need to weave that together. And based on this state, either bypass everything or go for this node, all right? How we're gonna do it? We already know we're using the filter for that. So I'll go to the filter, stream filter. Our gate this time will not be the value list which we manually crafted, but that will be the result of our formula, basically our boolean state. And I remind you that false is 0 and true is 1. So if I'll plug it into the gate, you're going to see that it by default takes the 0, 1, because this is the false. So when it's false and they are not identical, we make it identical, but removing the last element in this column. Here it is. So this one will be our stream 0. But what if they are the same? If they are the same, we do nothing. So basically we go in here, let me create a notch, and we'll just bypass it. So we go zoop, right there, bypassing all of this, right? Let me align it a little bit so it'll be easier to see. So kind of, I don't know, like this. We'll probably need to reorganize it a little bit later, but that's good for now. Let's do it like this. Maybe like this, a little bit shorter. All right, so that's correct. Let's go in and now check this and indeed increase the amount of points, and you're going to see it immediately pop up, and it never goes away. Because this result now is true, because they have the identical size. True, stream 1 in the output, our original geometry. All right, that's how you do this. All right, let me get back to 20 by 20 and let's continue. So now we have, I remind you, so this was our original grid, and you're going to see that we already constructed additional columns to the right and to the left. They are temporary, of course. We actually don't need these points at all. And we need only the sum of them. So from this new column, we need these points, these zigzag lines. And you're going to see that now they are not separate. They are a part of one. Very convenient. And above all else, I remind you once again, we have the same, absolutely the same data structure, right? So here, and the right column, which was this one, oh sorry, not this one, this one, has the same absolutely identical data tree, meaning that I can take element number 0, it will take the element number 0 everywhere. Number 1, it will take the element number 1, and so on and so forth. So now it's very, very easy just to connect the points between these two different branches. Now to do that, let me try to organize it a little bit better. So what I'm gonna do, I'll just kind of put that probably all down, maybe like this, maybe even lower, maybe like this. I need some space, maybe a little bit more. Okay, maybe this one will be enough. So I have this data tree and this data tree, and I need to pick elements now. So I want that some elements of these branch will be connected in the new data tree with these three. Like if you think about that as a hexagon, right? That will be the one part of the hexagon, that will be another part of the hexagon, and they will be connected. Yep, right now they are diagonal, we'll talk about that later. They will be connected. It will be like the long elongated hexagon, right? But it will be elongated hexagon only in 2D, because you can think about that as an wrapped pattern. But when we have a geometry, any closed geometry, because we are doing it for a closed geometry as an option, for example, a cylinder or blob, what it will do, it will wrap it around and it will merge the edges. And these lines, long lines, if you imagine that this is a hexagon, will shrunk to the one of its sides and it will become to be the proper connection. Of course, we will see it a little bit later. For now, we need to take the proper points. So from this block, we need to take the element 0, the point 0, 1, which one next? This one. Which one is this? 0, 1, 2, 3, 4, 5. The sixth element. So 0, 1, and 5. Remember, we'll start from 0, so it's not 6, 6, 5. 0, 1, 5. What's about this one? It's counterpart. It's counterpart connection. It will be 0, 1, this one, 2, 3, and 4. So we'll take these, and then these again. We'll construct a new hexagon. It will be identical for this connection, and this connection, and these, and these, and these, and these, so on and so forth. Let's try to do that. So let's start with the first batch. So I will go in and I will type a list item again, plug it here. This is the first element. That's correct. What's the next one? The next one is the element number 1, right? Like this. What's the next one? And that's pretty confusing right now. You're going to see all of the elements kind of picked here. And then I will tell you, well, we need the same point. But that's not the same point. I'll go, I need like 0, then the 1, and then I need this point. As it's already selected, but it's not. It's selecting it in these in the next branch, because they are overlapping. You're gonna see that here we don't. For example, here it's really visible. This is the first one, this is the last one, and I need this one for the group. How we're gonna do it? I will pick another one here. Let's go Control C, Control V, and this one will be the element, the indice of 5. This one, right? So first, then second, and then the last one, the third, right? And we have these 3 elements from one side. Then we need to do the same for the right, and we need to, using list items, take 2, 3, and 4, which means that I will have 3 elements here and 3 elements here, 6 nodes in total just to do it. And then I'll use a merge command, right, in this case, and I will weave them in specific order. So this one first, then goes second, then this one, this one, this one, and then this one, right? And then we need to do the same, because it will be slightly different for the pointy top. And instead of 6 nodes, I need to bring 12 nodes. Well, that's a little bit too much. I don't want to make all of this stuff in this way. I want to simplify the thing. Can I do that? Of course, because in the index, I can plug more than one value. I can plug a list. Who stops me? No one. So we're gonna go in and I can construct myself a path, and right here literally plug the values 0, 1, 5. Let's type 0, 1, 5. This is our indices. Remind you, right click, multi-line data, and I will type flat here because pointy will be different. And I'm gonna plug that into the index slot, and it will take 0, 1, and 5 automatically. All right. And then I'm gonna do the same for this one. But this time, I will go in and I will use a different list. So instead of a 0, 0, 1, 5, it will be 2, 3, and 4. Let's type 2, 3, and 4. Sorry, 4. Here they are. Perfect. So we have 2 groups which can now merge together, right? Not quite. You see, because we merged them together, we changed the order and basically can clamp them. So if in the original data tree, this one, the order was very specific, 0, 1, 2, 3, 4, we have like 0, 1, 2, 3, 4, then now when we look at this stuff, the picked elements, the data structure reconstructed. And I remind you, and I said it in the first video, in the first lesson, because this was really important, lists always start from 0. So if you construct a new data tree, it will start from 0, meaning that if you plug that in, you lost your order. Now these elements become to be 0, 1, 2, right? It was 0, 1, 5, and now they are 0, 1, 2, 1 by 1, 0, 1, 2. Same will happen here. Instead of a 2, 3, 4, they will become to be 0, 1, 2. And if you think that this is not an issue, this is very much an issue. And actually, that's such a big issue that it's a downside of a Grasshopper or the Grasshopper 1. And that's why in the Grasshopper 2, which I remind you, it's still WIP, it's still work in progress, it's still not the consumer version, still in development, this behavior will have an option to change, which is fantastic. But right now we need to deal with that. And now we have this kind of elements 2, 3, 4 lost their proper order, relative order, and become to be 0, 1, 2 again. What will happen if I'll merge one with another one, right? Well, let me tell you. Let me actually show you. I will merge the first batch with this batch. And how do you think, what do you think we will get? Looks like the parts of the hexagons, right? But these ones were free, 0, 1, 2. We will get connection like this order, first, second, third, and then this, and this. Does it look like a hexagon to you? Well, if I'll go to the display and visualize you the connection, everything but the hexagon, right? That's the wrong orientation, that's the wrong points. And you may say, well, then why we even connected that together? Let's separate them again. If we separate it again, then everything will be fine, right? Yes, but then we need a lot of nodes, like 6 nodes, like a 3 for one, 3 for another one, and another 6 nodes for the pointy top to individually pick them up. And we need a lot of gates to make it work. It will be just enormous construction, which looks very stupid and yeah, not ideal solution. But this one doesn't really help us also, because now we clamped them and we lost the order. How are we going to do it right now? Can we still use this? Well, the answer is yes, and of course, yes. Even though that we have these 2 lists and they lost their order, the proper order, we can't weave it one, like these one, then these one, then these one, then these one. We can't do that because we kind of merge that together. So we can't do it for the list item node, for the merge command. We're going to use a different tool. And this tool or this node called weave, and that's exactly what it's for. It's exactly for these situations. Now this node locates under the sets list weave. This one, it sits in the lists because we are operating with the lists themselves, not the branches. So it has these very specific inputs, a pattern and streams. It can be 2 streams or more, as many as you want. We need only 2 streams because we have 2 data trees, the first one and the second one. So what this node does, let me quickly visualize it using a metaphor, right? So imagine that this is our trees, right? And we have like some kind of elements here. I'll just put them like, I don't know, like this. Like whatever it is, is it a string, is it a number, whatever. So we have one here and we have another one there. They are identical in terms of their data structure, in terms of the element count within or list items, the same. And what the pattern, the weave node does is basically says, okay, give me please the 2 streams from this, which the first, the one of the streams will be 0, another stream will be 1. Okay, and then give me the pattern, and based on this pattern I will pick the specific elements from one list and from the other list, basically weaving them together in the order you want. And the count always goes up, so the first one, the second one, the third one, the fourth one, but the order you can change. For example, I want to take this one, right? This is the first element, then this one from one tree, the first and the second elements, and then, for example, this one, which will be my third element, and then this one here again, to basically kind of construct these connection, right? I'm gonna do it using the pattern. My pattern will be 0, because this is the 0 tree, the first element, then 0 again, this is the second element, 0 tree, then the third element will be from the another stream or from another tree. This is my another tree, this is the third one, and then back here. So using this as my pattern, I will pick these two from one list, then the third one from another list, and the next one from the original list, right? That's how it works. Let me show you how it works actually in practice. So we have this one and we have this one. Now we need to understand the proper pattern. Let me connect this one to the 0 stream and this one to the first stream, right? Let me hide that for now, Control Q, and I need to design myself a pattern. I will organize that just in a second. So what we need to do, we need to take the first element from the right side, from this tree. It will be the first element and then the second element. So it will be, as if you remember my sketch, it will be 0, 0. Why? Because this data plugged into the stream 0, so we will take it 2 times. Then we need to take this data, the second stream, because the third element will be this one, the fourth, the fifth. So we go in and we'll type 1, 1, 1, which means then we take 2 from this one, 3 from this one, and the last one here will be 0. Right? So 0, 0, 1, 1, 1, 0, right? Right click, multi-line data, and then we will change the name from panel to flat again. This is the flat one, meaning that for the pointy top it will be different. And we'll plug it into our pattern. Turn it on. We still don't know is it correct or not, so let's go in, display, points, plug that in, and that's exactly what you want to see. Now the basically it goes in from this one to this one, then here, 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 and it technically is supposed to go to the last one, but let me actually kind of visualize it a little bit differently. I will use the polyline instead. Polyline. We already used it before. It locates under, once again, under the curves, spline, polyline. I'll plug that here and let me close it. So it bites its tail. Right. Does it look like a hexagon to you? Well, I don't know. For me, yes, this is exactly what I want to see. Now, yes, it's skewed right now. It's angled. That's because of the amount of divisions we have. We will talk about that later. But it actually already forms me the hexagon. Now, imagine, once again, that this construction is wrapping around, which means that these points become to be on the kind of like they connected together, right? That means that when it wraps around, this line will become to be shorter, 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 basically become the same length. And it's like wrapped around hexagon, right? So if you connect that, just like abstraction, right? But if you connect it around the cylinder, imagine this is wrapping the cylinder, that will be the one side of the hexagon, that will be the another side of the hexagon. Imagine you're gonna kind of move it right there, here. And it will connect in the form of a hexagon. So yes, it is the proper result. I know, maybe it's a little bit inconvenient looking at the connection of this merging or this like seamless connection of a pattern in 2D, but trust me, having this picture in 2D means that it will be the proper one in 3D. Oh, we will see it when it gets to the surfaces. So this is a good result, and I'm actually I'm pretty happy because this is exactly what we did, what we wanted to do, at least for the flat top orientation. Okay, let me organize this and then we will move on. So how am I gonna do that? Let me think. So as we already have the gate with the values which we used here, you know, to pick the first element, and that was our first option or difference between the flat top and pointy top. I need to bring another one, and this one will be these two, right? So I'll go in, filter, plug the gate yet again. Let me organize this, and the first stream will be this one, and 2, and this one will be, oh, sorry, 0 and 2, and no, what I'm doing. So this one for the right side and this one for the left side, meaning that what we need to do is we need to, let me just reconnect like this. Let me go in and add another filter, plug it to the gate, and that will be for the left, for the first column, and this one will be this one. 1 and 2. All right, this is flat as well, like that. Right, let me now do the last one. So another filter to the gate. 1, 2, 3, 4, and now it will be this one. So 0 and 2 for the flat, and to the pattern we go like this. Right, let me condense it a little bit, and let me now realign the connections and realign everything else. So like it looks like a spaghetti code again, right? So let me quickly align that and quickly explain once again what we did. Yeah, okay, looks nice. Let me put it somewhere here because there will be something else here a little bit later. Let me plug. Let me just do it like this then. So put it to the right, put it closer like this. Let me move it down probably like this. Let me just actually do it like this. Or maybe even like this. No, it's too long. Let's do it this way then. Yeah, I'm just still I'm sorry for that, you know, but we really need to make it a little bit more organized, so it will be easier to understand what next will we do. We're gonna do it like this, right? Or like this. Okay, let's leave it like this for now, because we still need to do some additional modifications. And actually, last thing, let me just kind of put that a little bit up like this. Okay, so as you're gonna see now, we have a few sets of masks, every single one called flat, because right now we're working with a flat connection. So every single one of them does its part. This one specifies the elements in the right side. This one specifies the proper elements using the specific order in the left side, and this one weaves them together. And every single part of that will be different for the pointy top, but the script will itself stays the same. Right, now let me put the first mask here. Okay. Right, what's next? Well, now ideally, I can say now let's go and do that for the pointy top, but there is one more thing which I need to do first, and this is the ability to construct the actual final tree. And you're going to see that right now in the window that we get the proper result, we actually have two different trees. Because what is this? This is a separate branch, right? A separate data tree with branches with the same paths as the original last element was, right? We didn't change the paths, it's still right there. That's what gives us an ability to weave it, right? It's separate, and it's separate from original one. They're not the same. They are two different branches. So what I want is I want to bring them back together. So there will be a full assembled grid, not two different sets, but the one big set. Now let me go in and remove from the viewport something which you don't really want to see anymore. Now we don't need these one. We don't need these one. We don't need this first element as well. Here we don't need these one. We don't need the branch as well. This one we don't need, and this one we don't need. This one we don't need. The weaving pattern we actually need. And I'm just gonna hide this one as well. Even though this is the part of the indices, I just don't really want to be in my face. All right, let's hide these ones, and let's make the selection of the first element invisible too. Now, I would like to mention that when you work with a Grasshopper, it doesn't delete anything. So what you did, it stayed. It's just a question, do you want to visualize it or not, right? I believe you already understand that. So we're having this block and we're having this block. Now we need, of course, to merge them together. So how are we going to do it? Let's look at the data. So that was our new elements, and this was our basically the new connection overlapping the existing one, and that was the original data tree, right? Now the original data tree has the same, it doesn't have the same paths all around, but it has the same paths for the last column. Remember, this column here, right, this one, starting with 15 was the last one. That's why we figured it out which one it is, and we extracted that, right? So it starts from 15.2, 15.4, 15, and so on and so forth. Now if you'll compare the two with our last one, you will notice that they are identical. Not a surprise for you anymore. You would take this row, move it to the right, then move it to the left, merge that together. What happened with the paths? Nothing. Literally nothing. We used the same data structure. We didn't change that. And now we have a doubling, not only in the points. We need doubling in the points because this is the new hexagon actually, right? Which we can weave. But it has the same paths as these ones. Now, when we already did what we want, we don't need that. Because if I will merge two trees together, what will happen, and you probably remember it from the first lesson through data merging, is that when the paths are identical, elements will merge. Not stack one after another one, they will merge. So in the 15.2, there will be not 6 elements, but 12 elements, which completely destroy my hexagons. That's not what I want. What I want is that these new set of elements, this one, will be added after the original, because it will be the last now. Not 15 is the last, but the next one is the last. Which is the next one? Well, 16th, right? For example, we will still do some data management later and change the actual numbers, but for now what we need to do is we need to be sure that they are not the same, and this one goes right after this one. Right after this one means that we need to increase the path on one. So instead of a 15 whatever it is, 15 whatever it is, 15 whatever it is, it'll be 16 something, 16 something, 16 something. And then we can merge to construct the final data tree. How are we going to do this? Well, actually quite simply, and most of the nodes we already know. So first of all, as usual, what I'm going to do is I will take the paths. So statistics, plug that into the paths, look at the paths. This is the list of the paths. You already know that. Now what we need to do to take the first number, you already know, we're deconstructing the paths. And once again, I'm using quick callouts. I believe I explained it in the second lesson. Here we have this split, we extracted the numbers. The first part of the path, the second part of the path. What next we need to do? Pick them independently, all the first ones, all the second ones. So list item, once again, right now is the same as we did before. This is the first element, which will be the next one. The next one, of course. This is the first element, this is the second element, right? Now what we need to do is we need to increase the first one on 1, because it's not supposed to be 15, it's supposed to be whatever it is plus 1. How are we going to do it? Well, using expression again. So use expression and we will type x plus 1. That's it. So if I'll plug it here, I don't need y, it will be 16 now. Well, that's cool. What next we need to do? Now you see we have the indices for the first part of the path and the indices for the second part of the path. We need to construct a new path, not a mask. And because they are indices, this time I can go in and I will use the construct path node. I remind you it sits under the sets tree. Where is this? Construct path, right? And basically, I can use merge, right? Merge these one with these one. It will be the first element in the list and the second element in the list as these ones. Or I can just go and plug one and then hold shift and drag, plug another one. What do you have inside? The constructed paths. So instead of number 16 and number, well, 2, 4, and so on and so forth, we will now get the full path using this node, right? We don't need to concatenate as we did before. We can if we wanted to, but it's no need, because they're actual indices. They're not a mask. Cool. What next we need to do? Now we have these new paths. Well, that's good, but our data tree still has the original ones, right? So we change it somewhere else, somewhere here, right? Separately. But the paths for this tree is still the old paths. Now we need to somehow replace the paths. So we take these ones, the old ones, and want to replace it with the new ones. Can we do it? Yes, there is a node for that called replace paths. Now there are 3 inputs: data, search, and replace. Data is your actual data tree, whatever you have, points, object, geometry, whatnot. Plug that into the data. Search is your paths for this tree. For this tree you plugged into the data. So we need these paths and we need to do it separately. If I'll plug it like this, it will give me an error, it will not work. I need the actual paths as a list, and the statistics nodes give me those. So this is the list of paths. Let me plug that in. Oh, sorry, wrong input. Right there. And replace. Replace is the paths I want to replace it with. Now these are the paths I want to replace it with. But there is a problem. Data structure, of course. This is a list. This is a grafted list. Meaning that basically if I'll try to do it, I basically asks to replace all of this by this, all of this by this, all of this by this, and so on and so forth. I don't need that. I need to replace this by this, this by this, this by this, and so on and so forth. 1 to 1, 1 to 1, 1 to 1. So our data structure is supposed to be the same. And if I'll plug it right here, I will get an error because of that. So what I need to do, correct, just flatten the list. Let's make it flat. This one already flat, so flatten. Now they will work one by one. This to this, this to this, this to this, and so on and so forth. What are you going to do? Plug that into the replace. And let's look at the result. It was 15 something, 15 something, 15 something. Now it will be 16 something, 16 something, 16 something. You see? Now we have a new paths. Very simple. So when we did that, the only thing left, well, not the only thing actually, there's a little bit more things to do. But what we will do now to finish with this data management is we will take this new data tree, because the output here is actual data with the new paths, and merge it with the original one. And now they will merge perfectly. This one will go next after the original one because it has a bigger path, or the deeper path, the proper way to say it. So how am I gonna do this? Let me just kind of maybe realign that, maybe something like this. All right, like this, right? Kind of like that. Or should I really bring a notch? Well, I don't know, let it be like this now. So now I will go in to my original object, and I will go in and I will use the not the original object, the original tree. I'll use a merge command. I plug my original tree. Remember, I can go through these notches tossing me the data, basically all of these points. So I will merge them. It doesn't matter at which slot I plug that because they have the proper paths there. The final one is lower on one than this one, so they will merge. And I will merge them with this one. Once again, order doesn't matter in this case. And we go in, and now we have the full data tree, which ends with 16. So we took the original one and add up this part as a closure for us, right? Let me organize it a bit because it looks like shit. So plug it right there, move it to the right. Let me do it like this. Let me push it up maybe to make it a little bit more compact. I'm gonna take this one, by the way, make it a little bit more compact. Oops. Now, if you don't want to bother with all of these kind of arrangements, don't worry. Well, in the next lesson, I will give you, of course, this, so you can download that if you want. So now we have the proper combined set, and let me quickly check that. So I'll go in and plug the vertices in and turn that on. Perfect. This is exactly what I want to see, although it's diagonal, but we will address it at the end of this session. So before we go in and just do the same for the and tweak the script for the pointy top orientation, there are a couple more things which I want to do. Now, first, I need to actually add a switch, because right now the script just based on the hex type go in and construct a merge. What if I don't want to merge? What if my my grid don't need to be merged and wrapped around? Well, there are of course situations where you don't need that. Sometimes you want that, sometimes you don't. So we need to construct a switch for that and just bypass all of that if we don't want that. So let's do this first. I will use the value list. We already used it before to set a specific variables, right? Let me go and change that. So the first one will be closed. Let's say it will be 0, and the opened will be 1. Why not? Right? Let's delete this. We don't need that. And let's give it a name. What name we can give it? Let's stay. That was the hex type, so this one will be structure type. For example, I don't know. You can call it the way you see fit, right? Then we go to the filter. Bring stream filter. This will be my gate. And there are two outputs. Now the closed means that we go in basically for all of that, and we will plug that into the stream. If I don't want that, and what if I don't want that? If I don't want that, then I need to take this block right there. So I put a notch here, and basically like this, right? And basically bypass it. Like, no, please take all of this stuff and don't use it. Just take my original grid, take my original grid, and when it's opened, just use that. And you're gonna see right now we don't have any additional connections, right? It's not not there anymore. Let me clean up all the nodes which we don't want to see. Let's see how we're gonna simplify this, because there is one more thing which we need to do. Let me remove the weave. We already constructed that. Looks like we removed all the unnecessary ones. This is the paths. I'm gonna close this one again. The data we don't need as well. Yeah, so if I will hide this one, yeah, we'll remove the points, hide this one, remove the lines. All right, cool. So before we move on, now the last thing which I really want to do before we finish it with the additional fix for the pointy top is I would like to add a centroids. Now, what is a centroid? So you're going to see that our hexes now are completely empty inside. And you may say, well, yeah, that's exactly what the hexagonal pattern is, right? Yes, you're right. But as we are building a script which works with through multiple surfaces, through the single surface, it constructs hexagons, pointy top and flat top, it can rotate it and so on and so forth, we can add up additional functionality to that, which is kind of very cheap to add, but really powerful in the long run, because we can do a lot of different constructions based on the hexagon. For example, if we have a centroid, we can place geometry here. First and foremost, we have like a list of points if we wanted, only the centroids. And of course, we can construct a triangles or a quads inside, on demand, of course, if we wanted to. But for that, we need a centroid. And I want to bring it here in this lesson as well. How are we gonna do that? Well, if you I will remind you that originally we had a grid of points which actually has the centroids. Here they are. But then we filtered it and now they're gone. I can of course go back, take the specific points, merge them together using data management again and do all of that. But because we are working in 2D, once again, that's one of the reasons why we're not working on the surfaces right from the get-go. It's actually much simpler because it is planar, and the point in the middle will be what? Correct. It will be the average mathematical average or arithmetical mean of all of them. So that the arithmetical mean of all the points will be the center point, as well as the arithmetical means of all the numbers will be the average number, right? I believe this is something you know from school. Now the only problem is that we need to plug a lot of data here because it's the sum of them divided and then the add of all of the elements divided by the sum of them. But we have a lot of elements because every single point described by, correct, 3 numbers, and we need to do it component by component. And that's quite tedious to construct. Once again, just too many nodes. Deconstruct, no, deconstruct component, take the points, do an absolute, and blah, blah, blah. Instead of that, we actually have a dedicated node here. If we go to the math utility, we will find the node which we're actually looking for. It does everything, but for us, it calculates basically the average without us needing to deconstruct the points and do component by component operations. So we plug here a number, a set of numbers, and then we will get the average of those numbers, right? But these points are points. And this is an input supposed to be a number. Is it a problem for Grasshopper? No. Grasshopper understands that the point is a collection of 3 values. As I said, it can be treated as a vectors, it can be treated as just a numbers, and it automatically detects, deconstructs, sums them up, does everything you need to do to create the average. So you can plug points here, and in return, it gives you the average point. It will connect everything together. What it generates from the part of the Grasshopper. So if I will plug it right now, right here, I will immediately get myself a centroids. That's it. And guess what? It has the same data structure. Of course it is. Why not? It's just only one element per branch, but the paths, of course, are identical to these ones, which is fantastic because I can merge them together now. So they will, all of them sits that every centroid will sit into correspondent set of relative points, right? So like a full confined and enclosed system. Now, I would like to mention right now that the average means, of course, can work with the numbers. So, and this is something which we will do in the future. So let me just bring it here and just mention one important thing, that even though that average is supposed to work with the numbers, if I'll plug that in, you're gonna see it really gives me an error. What? It works with points, doesn't work with the numbers? Why? Because the panel, the sum of the nodes, doesn't really interpret the data properly. And for that, we have a whole list of very important nodes, which I didn't even touch yet, but we will when it comes to the surfaces, which serves a lot of purposes, a lot. They are very, very useful for multiple of operations. And one of them is specifying the type of data. So if I will go in and I would say that this data is integer and plug that in, it will work and give me the average number, which is free, of course. So why I'm telling you that? I'm telling you that the average means works with points. We are using it right now. It works with numbers, of course, but through additional component. We will figure out why it is the case a little bit later and why do we really need them. But just keep in mind that average here, average exists. It just has a slight oddities. In our case, it doesn't really matter because we're working with the points and Grasshopper understands that really, really well. All right, so we have this average value here and we get these points. Now we somehow, we already constructed ourselves a grid. What are you going to do next? Well, we need to add it up. So we already have ourselves a grid of points and we toss it to here, right, before we merge. So before we do that, we plug this, or maybe even just, let me just do it like this. Whoop. Like that. So we get ourselves the average mean. This is the new points. And we need to merge them with our original base grid, this one. So we'll go in and I'll type the merge. The order matters this time. These one's supposed to be first. It will be easier for us. And the grid itself will go second. So first, second, like right now. So if now I will pick the first element in the list, it will pick me the centroid. Here it is. And then we go, that will be 0, then 1, 2, 3, 4, 5, and so on and so forth. Cool. Now when we did that, we can, let me just clean it up a little bit. Let's plug that right there. Let's move it closer here probably and connect. And we have a lot of issues right now. Let me just kind of hide that for now so it will not be that confusing. So we have the new object or the new data tree with a centroid, right? But we don't have, and this is very important, that, let me just kind of hide this. If I will turn on these set of points, which we constructed methodically to create the proper connection and bite its tail, we don't have a centroid for them. So we have the centroid right now only for original ones, meaning that when we wrap around, it means that most of the points will have centroids except of the last kind of column, right? Which basically merges everything together. It will not have the centroid. Well, we need to have a centroid. But where is the centroid? You see, if I will look at this one, at this connection, right? Once again, let me just bring the polyline here really quickly and unplug the polyline here. Well, where will be the centroid from these points? In the middle, right? So if I will use the average here and plug that in, it will place it me right there, right here. Is it correct? No, it's not correct. Because this is just a temporary line, temporary connection. When you wrap around, it will not be this length. It will be shorter. But the point will stay the same. Where we need the point? Here. Specifically, we need the point. And we know where it's supposed to go because we already constructed this temporary part. You know, the part we took this first batch of points, right? Which we moved to the right. Here it's where it's supposed to be, right? Yes, fantastic. Let's do that. So I will use the average again. And of course, there is another ways to find the center, right? You're gonna construct the line, divide the line or find a center point of the line, and this is how you're gonna get that. But it's just easier in 2D to use the average, right? So this is our point, right? What we need to do, we need that this point, as well as with the original grid, was first, and these ones go second. So we need to merge that, right? So what I'm gonna do, let me just kind of create a notch, plug that here somewhere. Okay. So, and there is the problem right now because here, this new connection already changed its path. It was 15, now it is 16, but this one is still 15. So we need to do something. What can we do? Exactly, we need to actually merge these two together before we do modifications with the path. How are we going to do it? Well, very simply, we use the merge command, and we will do the same. This comes first, and this comes second. So I'll hold, first I will hold Control Shift, click and drag, and switch it right there, and we'll plug this one here. And even though that it looks strange, trust me, this is exactly what we want. Let me hide that for now, so it wouldn't be really confusing. Let me align it, and then I will show you what we did. So let me put it maybe here, like this. Let's put that up, like this. Let me align this one. Okay, let me remove the merge, let me remove the average, let me hide the average here and here as well. So I'm using Control Q once again. So, okay, here is our new structure, and the first element in the list is supposed to be the centroid. Let's check. Yes, it is. Meaning that if I really want to construct a polyline, it is supposed to be the polyline. It shouldn't be going through the centroid. We will fix it a little bit later in a second, but what's important now is that they are now merged together. They merge together first in the same way as the original grid does with the centroid, and now we have the proper data structure, but instead of 6 points, we have 7 points, and the first point, as well as here, is the centroid. So when we merge them together here, now we have the full grid, and the first element of the grid, let me just kind of hide this. So that means that the first point of this grid will be the centroid. Let me show you. Here it is, right? But just one thing to note is that as we are in the opened, our switch set to opened, we don't see the centroids here. Why? Because we bypassed everything. We don't have these additional duplicates, right? But the moment we switch it to closed, now we have our duplicates and we have our centroids where it's supposed to be. If I really want to construct the polylines now, just to visualize it, it's really easy for me to do. I will first, now I can't do it like this because it goes in the wrong direction. I will use call index, and I'm using it temporarily just to visualization. I will call the first index in the list because this one will be, right, remind you, our centroid. Plug that in, right? So this element is a centroid. This element is a centroid. I don't want them. So I want them, but not for the polyline. So I'll plug that in here. Now it's become shorter. I'll plug that into the polyline. Here is my line. Centroids are not taken into consideration. And this is my centroids, right? Very convenient. So let me just... Now, this is, of course, just a temporary visualization. We don't need this. We need a much more complex solution a little bit later. It's just for you to see, well, something, okay? All right, so now when we edit up the centroids for things to come, because once again, we need to weave optional additional geometry here. It'll be really, really nice if we will have this option, and we will have this option. We need, before that, we need to, of course, finish our main script. Now the script itself is ready, but we don't have the solution for the pointy tops. So let me quickly clean this up. Let's see, what do we have here? We have these points somewhere. There's these ones, hide them. All right. Okay, so this is the original grid with the centroids, right? And this is its, this is its polylines. Now I switched that first to opened, right? And let me now go in and change the type of the hexagon from flat top to pointy top. So now we go to the point, it doesn't matter which one I pick, like this one, pointy top. Now it looks like nothing changes, right? It's just the same. But if you look at the script itself, something broken here. So basically all this stuff doesn't work. We are in the opened, meaning that everything is bypassed. If I'll switch it to closed, you know, it doesn't really do much because this one just doesn't have the proper data, right? So it basically takes the stream 0, and the stream 0 is our original one. So this one doesn't work at all. Well, the reason why it doesn't work is because we don't have the proper masks for our points, right? Now remember that here, if we'll plug the value 0 into the index, we're going to see that we are picking, because this is the first thing which we did. We take the elements, right, and we move it to the right. Remember, this is our first step. Take the last column, and we're calculating the last column, of course, the same way, and then we move it to the right. But to move it to the right, we need a different starting point, because right now it moves right there. It shouldn't be here. It shouldn't be right there. Stagger differently. And even though that the shift to the element 2 is correct, the starting element is not correct. What is the proper starting element for that? Let's take a look. So what is the order for these hexagons? This is the first point, this is the second, the third. How I know? I already mentioned, because this is how we weave it using the relative item command. And if I plug it here, you're going to see that indeed this is the first one, the second, the third, and so on and so forth. So knowing this, we need to somehow take this hexagon and move it one up, same approach, right? From where to where we need to move it, right? So we need to take the element number 0, 1, 2. Let's think about that. So if it's supposed to go here one up, we probably will take, let me think. We'll take the element number. So this one will stay the same. It will always be 1, 5, 0, 1. So I will probably take the element number 5. No, sorry, 4. Yes. So 0, 1, 2, 3, 4. Yeah, this is the fourth, not fifth. So this one. So what I will take this. Let me just kind of hide this. I will take this point, right, and move it to this is the point number 4, 0, 1, 2, 3, 4, or the fifth point, right? Just made a mistake and recalculated the actual order and the indices. So this is the fourth index, or the fifth point, and we will move it to 0, 1, 2 to this one, like this, and it goes one up, and it is. So what I need to do, I will go in and change the name of this to pointy, like this. Let me expand it a little bit and plug that in 1 and 3. All right. And now do it this way. Okay. So as you can see, the object, the input 1 is in effect. Input 3 is not in effect because we are in pointy top anisotropic, not in the pointy top isotropic. But for the script, it doesn't really matter. Of course, it's about the proportions. So let me align that a little bit and let's move on. The next one is this section. This section basically where we take our already oriented staggered column, and we need to pick a very specific points here. What points we need to pick? Now the order is the same: 0, 1, 2, 3, 4, 5, 6 in total. So we need to merge it to the block to the left, and here you're going to see it's constructed, of course. So which points we're supposed to pick here and which points we're supposed to pick here? Not these ones, because if we'll take 0, 1, 5, it will be 0, then 1, and then 2, 3, 4, and 0, 1, and 5, which is this one. These, and these, right? Well, this and this is correct. This is the part of the left hand, but this one definitely off. We don't need this point for the right side. We need only two. This, and then these, and these. So both of the masks for the right side and for the left side are wrong. This one's supposed to be only 0 and 5. Let me go multi-line data and change that to pointy again. Let me shrunk it like this and plug it here. All right. Perfect. This is the proper points. And here we need to take these, and these, which means that it will be, oops, sorry, it will be Control-C, Control-V, the type again, pointy, and this one will be 0, 1, it will be 1, 2, 3, 4. So not 2, 3, 4, but 1, 2, 3, 4. So 2 points from the right and 4 points from the left. Let's go, plug that in. Okay, let's take a look. Perfect. 2 here, 2 here. And now the last but not least, oh, it looks like shit. So I align that a little bit better. Okay. Last but not least is the actual weaving, right? So we need to weave this to this, which means that we will take, using our weave pattern, if this is 0 and this is 1, we will take 0, 1, 1, 1, 1, 0. We have a different set. Let's change that. So we go in, type pointy, and we will type 0, 1, 1, 1, 1, 1, 1, 1, 1, and then 0. And it works. Nice. Let's look at this stuff. Yeah, perfectly. Perfect, perfect, perfect. So you're looking at this construction like, what the hell? But this is a hexagon, right? Once again, if you will start wrapping around, these lines will shrunk to the same size of the side of a hexagon, and we will have, like, imagine like this one, we move it here to these points, right? And you will get yourself a hexagon. It's just this representation in an unwrapped state, right? All right, nice. Now let me clean this up and address the issue with the skewing. Right now we don't have a skewing. We can, and but for the pointy top, or sorry, for the flat top, by default we have this kind of problem with the skewing. Let's address this. So first of all, let me kind of make it a little bit more convenient. I will just compress the masks, because I actually don't really need to look at them all the time. We will not change them. This is hard-coded, so let's do it here, here, and here. We move it to the left, like this. Oops. Let me hide the stuff I don't want to see. All right. Is it correct? It is correct. Let me push this one up. Okay. So next, let's address the problem with the skewing and actually talk about that a little bit. So yeah, this is one still there. Which one? Let me delete this one. Oh yeah, of course. So, and as you said, you see, I'm removing from the viewport everything which is overlapping and duplicated, like all the process I don't need, because I need only these ones, right? Oh, sorry, to be specific, this one. This is the actual proper structure, right? A final one. So, what's the problem with these skewings? Now, here there are no problems. When we are at anisotropic pointy top with the specific divisions 20 by 20, everything is correct. It wraps around, it perfectly matches. But if I will switch to the flat top, you're going to see that we actually don't have it. Let me just remove the... remove these ones like this. I don't wanna visualize the centroids for now. Just additional clutter. So you're gonna see that it actually has a diagonal connection. Will it merge? Yes, but it definitely will not be the proper merge because we will have this kind of shift, right? Shift in the period. Now the reason why we have it is because we don't, or the actual even and row and odd rows, or sorry, the beginning and the end of the pattern are not in phase. And they're not in phase because this is the staggered pattern, and we can define the phase by the amount of divisions, so that this pattern perfectly wrap around. Now, once again, in terms of the geometry, it will wrap around, But of course, we will have this kind of shift. It will look odd and not desirable. So we want to have the same kind of perpendicular structure, right? Or parallel structure. And for that, we need a very specific amount of rows and columns. In our case, of course, as we're going in x directions, we are talking about the columns. This is x. So if I will increase the amount of x, you're going to see that right now it become to be the proper sections, and all of them are, you know, horizontal or parallel to each other. So this is the proper structure. And we need to add 2 additional rows, right? 3 additional rows, we just add additional space. It doesn't really do anything for us. This one will not. Then this one shifting again, right? This is the wrong, this is the wrong, this is the wrong, this is the right. And same can be said for just the divisions. You know, maybe we don't really want to add additional rows through our ability to add additional rows below the normalized domain, but actually going to change the actual amount of divisions. And you're going to see not all of them are actually working, because we need a very specific set, the specific staggered pattern that so they work. The amount of elements supposed to be identical, and the period, the staggered period, is supposed to be identical. Now the question is, can we predict that? And is it the problem only for the pointy top? Now let's start with the last. Is it the problem with the only with the flat top? The answer is no. If you switch to the pointy top, and you will start moving that, and you will have a completely different result. Now this the odd numbers here, right, are actually giving you a problem, right? You see? And it goes through 1, 1 to 1 to 1, 1, 1, 1, 1, and the flat top, you know, it just doesn't do that. You see, this is the same, and bam, 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 just extending. The behavior is different. Behavior is different because this is different types of weaving. We differently weave the hexagons, which is natural for each of them, right? It sounds strange, I understand, but you just rotate the hexagon, you know, 30 degrees, and it's just such a different behavior. But if you understand it, look at that closer, you will understand why it is the case. So no, this problem persists for both, for flat top and for the pointy top. Now the next question, can we solve this? And the answer is yes and no. Depends on what I was thinking about the solving. If we, for example, know that we will use this geometry only on a cylinders, then to extent we can predict the sequence of numbers, right? But of course, it depends on the size of the hexagons, how many hexagons will fit, and so on and so forth. We can do it. We're going to create a very specific sequence of numbers, which we know that for the you know, pointy tops, it will behave this way every single time, and for the flat top, it will behave this way every single time. So based on the size of an element, the radius of a cylinder, we can predict the specific sequence of numbers and just use it in our script. It'll be a pretty beefy construction, but it is doable. However, this solution is a solution for whatever closed geometry or open geometry you have. Well, we are right now talking about the problem with joining, so it's a closed geometry. For every random closed geometry, like a blob, for example, or I don't know, some kind of a I don't know, semi-cylinder, right? Or maybe just organic shape, or maybe some random sculpted element like a grip for a gun, for example. It's not a perfect cylinder, right? There can be a lot of geometry, it can be a lot of edges and be curved in a different manner. We can't predict that. So we technically just don't know. But it's not an issue because we know how to quickly solve it. We put our pattern in, we see that it's skewing, you know, we're adding up a couple elements. Same with the pointy tops. We see that it's skewing on our geometry, any random geometry, you know, like, okay, I will just kind of add additional two. Now, here it's just working, like I say, it's just like this, right? Or sort of like this. Like, okay, bam, it's done. So that will be, even though that this is not purely automatic, it's very easy to tweak just by using the slider, and it works across absolutely any type of a geometry. So you don't need an additional construction which works only for the perfect cylinders, like for example, right? No, it works everywhere. We just need to go in and make sure that we have the proper period using our division slider or additional X and Y division slider, right? So one or another. Anyway, this is how we actually constructed ourselves an ability of the script to add the optional feature that allows a hexagonal pattern to wrap onto itself seamlessly. And this is how we did this. I will switch this to opened mode, and in the next lesson we will proceed with actually, as we already have the centroids here, we will proceed and giving ourselves additional optional feature to fill it with triangles and quads, as well as switching the direction in which they rotates. Right. All right. Thank you very much. Thank you very much, guys, for watching, and I will see you in the next one.